वेलकम टू वी लर्न में आपका स्वागत है। सब्जेक्ट ऑपरेशन रिसर्च सेशन नंबर 7। टॉपिक टू बी कवर्ड इन सेशन: इंटीजर प्रोग्रामिंग, इंट्रोडक्शन, सम इंटीजर प्रोग्रामिंग फॉर्मुलेशन टेक्निक्स, यूनिमोडुलैरिटी, कटिंग प्लेन मेथड्स, branch and bound method. And now introduction. A linear program with decision variables restricted to integer values is called a linear integer program. The integer restrictions on decision variables in a LP framework may be inherent in the problem situation. There are also situations where these restrictions may be imposed or engineered by the analyst. Integer variables, specifically those which can take a value of 0 or 1, have been used in many problem situations to provide modeling capabilities beyond those available in linear programming. LP formulation techniques. Integer programming formulations of problem situations do not pose problem when the variables inherently are discrete in nature. Problems arise in situation where direct LP or IP, that means linear programming or integer programming's formulations, are not possible. Codification of variables are helpful in such situations. We first present a direct integer programming problem formulations of a problem situation. This is followed by two other situations that require codification and transformation. Situation 1. You have landed in a treasure island full of 3 types of valuable stones: emerald, ruby and topaz. Each piece of E, R and T weight 322 kg and is known to have a value of 431 crores respectively. You have got a bag with you that can carry a maximum of 11 kg. Your problem is to decide on how many pieces of each type to carry within the capacity of your bag so as to maximize the total value carried. The stones cannot be broken. And our formulation exercise: define the decision variables. x1 equal to number of emeralds to be carried, x2 number of rubies to be carried, and x3 equal to number of topaz to be carried. Express the objective functions and the constant in terms of the decision variables. The total value carried as a consequences of x1 of E, x2 of R and x3 of T. Under the assumptions of linearity is 4x1 plus 3x2 plus x3, and as per the problem this has to be maximized. Formulation exercise 2. Maximize 4x1 plus 3x2 plus 1x3 subject to 3x1 plus 2x2 plus 2x3 less than equal to 11. x1, x2, x3 are all non-negative integers. Situation 2. A company has to decide on the production plan of an item for the next 3 periods so as to meet the demands in different periods at minimum cost. The relevant costs are the production and inventory carrying cost. In any period only if production is undertaken, then a cost of rupees 5 is incurred. The variable cost of production is rupees 5 per unit. The inventory carrying cost is rupees 1 per unit per period and is levied on the inventory at the end of any period. Assume that the demands for the upcoming period are D1, D2, D3 and the beginning inventory is known to be 1. Formulation exercise: decision variables. x1 equal to number of units to be produced in period 1, x2 equal to number of units to be produced in period 2, x3 equal to number of units to be produced in period 3. I1 equal to number of units in inventory at the end of period 1, I2 number of units in inventory at the end of period 2 and I3 equal to number of units in inventory at the end of period 3. Formulation exercise 2. The problem in formulation becomes evident once we try to write the production cost functions in period t. Production cost in period t, C says equal to S plus Vx if x greater than 0, which is equal to 0. The objective functions can now be expressed as minimize S y1 plus y2 plus y3 plus V x1 plus x2 plus x3 plus I1 plus I2 plus I3. The constants are essentially the material balance for each period given by opening stock plus productions minus closing stock, which is equal to demand and can be expressed as follows. I0 plus x1 minus I1 equal to D1, I1 plus x2 minus I2 equal to D2, I2 plus x3 minus I3 equal to D3. The other conditions are with respect to the variables yt and xt. Xt for all t are non-negative integers, yt equal to 1 if xt greater than 0, which is equal to 0 otherwise for all t. Situation: consider a tailor facing the problems of sequencing 4 stitching jobs given by different peoples. All jobs have arrived simultaneously and he has only one stitching machine. From his experience, it is possible for him to make a fairly accurate estimation of stitching time of the jobs. Each customer has specified a date by which the respective job is to be delivered. The tailor wants to determine a sequence so as to minimize the average tardiness of all the jobs, where tardiness of any jobs is given by maximum. It is also agreed that once a job is started on a machine, it cannot be taken out before completions. In our formulation exercise, assuming a datum of 0 time for starting the work and an arbitrary numbering of the jobs as 1 to 4, let x1 denote the starting time for job 1 from the datum I equal to 1 to 4. If the processing time for job I is denoted by pi, then the completion time for job I equal to x1 plus pi. If d1 denotes the given delivery date for job I from the same datum, then by definition tardiness for job I maximum 0 xi plus pi minus di, and the objective functions maximum, minimum or maximum 0 xi plus pi minus di. Equation 1. To convert the above into linear programming or linear forms, we define yi equal to maximum xi plus pi minus di. Then I is equivalent to minimize yi subject to yi greater than equal to 0, yi greater than equal to xi plus pi minus di. And our formulation exercise 3. To express this in terms of the decision variables, we note that if I precedes j, then completion time of I has to be less the starting time for j. And our formulation exercise 4. xi plus pi less than equal to xj. Similarly, if j precedes I, we can write xj plus pj less than equal to xi. Either 3 or 4 should be active, and in our problem, as there are 4 jobs, 4c2 such pairs of constant will be there. Once again, this either or conditions being not linear, we take recourse to integer variables sij, where sij equal to 1 if job I precedes j, if j equal to 0 if job j precedes I. Then either 3 or 4 can be replaced by msij plus xi minus xj greater than equal to pj. Then mi minus sij plus xj minus xi greater than equal to p1, where m is a very large number. Equations 2, 5, 6 together with the restrictions on variables xi and sij give the required formulation. Unimodularity. An IP model cannot be solved as an LP. because if fractional values are obtained in the solution, rounding off may not be possible or desirable. For the purpose, let us consider the following IP problems. Pi maximize C1 x1 plus C2 x2 plus C3 x3 plus and so on Cn xn, subject to A11 x1 plus A12 x2 plus A13 x3 plus and so on A1n xn equal to V1, and then x21 x1 plus x22 x2 plus x23 x3 plus and so on A2n xn equal to V2 and plus and so on. Then AM1 xn plus AM2 x2 plus and so on AMN xn equal to Bm. x1 x2 x3 and so on xn are all positive integers. From LP theory, we know that given m equations and n unknowns, m less than n, we can set n minus m variables to 0 and solve for the rest of the m unknowns provided a solution exists. The n minus m variables that are set to 0 are called non-basic variables and the rest m variables are called basic variables. The number of different ways in which the m basic variables can be chosen from among n variables is known to be NCM, where C is a combination constant. This implies that a total of NCM combinations of constant sets as in P2 can arises. However, a solution may not exist for all such sets. When a solution exists, it is referred to as basic solution. The class of basic solution with all non-negative values of the m variables constitute a basic feasible solution called BFS. Unimodularity. 4. To understand when the BFS will be integer, we first now note that the non-basic variables being all set to 0 are integers and as such to do concern us. For finding out the conditions under which all the basic variables are integers, we first state the conditions in the context of the problems Pi. Proof of the conditions requires familiarity with matrix algebra and is presented in the appendix of these sections for those who are interested. Condition: if the matrix of the technology coefficient denoted by A with elements A to E is totally unimodular, then every basic solution of Pi or P1 is integers. We denote that in P1 the matrix A is given by A11, A12 plus and so on A1n, A21, A22, A23 plus and so on A2n, and then AM1, AM2 plus and so on AMN. Proof of condition 2. Rules: an integers matrix A with all elements equal to 0, 1, minus 1 is totally unimodular if each column does not have more than 2 non-zero. The rows can be classified into 2 subsets such that if a column contains 2 non-zero elements with the same sign, one element is in each of subsets. If a column contains 2 non-zero elements of different sign, both elements are in the same subset. Cutting plane methods. The basic steps involved in the methods are solve a LP. To start with, take the IP problems with integer restrictions relaxed. Check whether the optimal solution is integer. If yes, stop. The resulting solution is the required one. If no, go to stop. Then third, generate a new constraint from the fractional optimal solution obtained in first. The constraint is created so as to rule out of fractional values obtained. Without ruling out any integer solution to the problem, add the constraint to the LP in first and go back to step first. The methods involve solving a LP at every iteration. The approach is to reduce or cut the solution space in every successive iteration, ruling out the current fractional solution while ensuring that no integer solutions are excluded in the process. The process is continued till an integer solution is found or infeasibility occurs, as the constraints are essentially used to cut the solution space. These are referred to as cuts, and the methods is referred to as the cutting plane methods. Now, branch and bound. Branch and bound is generic methods for solving a class of optimization problems. The optimal solution is selected by successive partitioning of the set of all possible solutions into two mutually exclusive and exhaustive subsets, and establishment or establishing limits for each set such that all solutions in the sets are worse than the limits. The first part of the procedure involving partitioning is called branching. The second part of establishing limit is referred to as bounding. And now do it yourself. Question number 1, explain cutting plane method, and question number 2, explain unimodularity. And that's it from session number 7. Thank you.